Thank you for attending today's virtual seminar titled Using Electrical Conductivity Measurements to Optimize Irrigation, presented by Dr. Doug Cobos.
Good morning and welcome to today's virtual seminar. Today we'll be talking about using electrical conductivity measurements to optimize irrigation. And we will, of course, start out talking about why we would care about optimizing irrigation and why we would care about using EC to do that. Then we will spend quite a bit of time talking in some detail about the various measures of electrical conductivity. There's a lot of confusion out there about the differences between bulk electrical conductivity, saturation extract electrical conductivity, and soil water or pore water electrical conductivity. So we'll lay out those things and how you measure them, and then we will get into how you could use some of these measures of the soil salt status or electrical conductivity to do a better job of irrigating. So let's go ahead and get into it. It's pretty well known that the commercial grower or the farmer really is driven by the bottom line. Those of us that are in academia can do all the research we want and show that things are better for the environment, but if the research that we do or the techniques that we suggest don't help the bottom line and help the profits of the commercial grower, then the chances of those practices being adopted are extremely small. So I think we need to tie some of this applied research into that first and foremost goal of every commercial grower, and that is to increase the yield or quality of the crop and therefore increase the profits. And all of the other goals that we talk about here today really need to tie back to that, or this is a lot of conjecture and not a lot could come of it. So how do we accomplish that goal of increasing profits? Well, first of all, we need to keep the water at optimal levels for plant growth. If we have the soil too dry or too wet, then we're going to decrease yields or decrease quality, and if that happens, then that of course decreases our profits. Also, if we over-irrigate, we tend to lose nutrients. We tend to lose fertilizer from the soil, and those lost nutrients are of course lost money. It costs a lot of money to put nitrogen and phosphorus and potassium and micronutrients on the soil, and if we flush those through the soil by irrigating carelessly, then that doesn't help the bottom line at all. It also costs money to pump water, so if we can decrease the pumping costs or decrease the amount of water that we apply, then that of course affects the bottom line. In this day and age, now that we're starting to get into some water shortages in some of the irrigated agricultural areas of the world, there are now some regulations that are decreasing the amount of water that can be applied to the crops, and of course that really ties into the bottom line. So water use is a very important factor that we're gonna do a lot better at if we control our irrigation optimally. And finally, we do need to maintain soil productivity. So 200 million hectares of ag land are irrigated globally, and this produces almost half of our food on only 20% of the acreage. And so if we don't do a good job of controlling our irrigation and we have salt buildup or salinization in those soils, then we will see drastically reduced yields, and sometimes these problems are hard to remedy. And so if we don't irrigate properly and we build up salt, then we get into problems with sodium toxicity or even osmotic stress if our salt concentrations are too high. And so maintaining a proper leaching fraction and flushing those salts through the soil is important for long-term sustainability of our farming practices. So all of these things, I think, tie back into the bottom line, into the profits, either short-term or long-term. So what are some of the common irrigation strategies that growers will use to schedule their irrigation? Well, I think that probably still the most common one is to do what Dad did. Okay, either irrigate on a schedule, or go out from time to time and dig a hole and grab some soil and feel it and see if it seems like it has the right soil moisture. And these are kind of tried and true methods, but they are certainly not optimal. A lot of times in the quest to maximize yields, farmers will put on as much water as they think is enough and then just add a little extra for a little margin of safety there to make sure that they don't under-irrigate. And the thought there is that, well, if a little is good, then a little bit more is better. That, of course, isn't always true. If you waterlog the soil and go anoxic, then that has some pretty serious consequences to crop yields. Also, if you're putting on too much water, that means that you are pumping extra water and paying for the electricity or gas to pump that water. And you're also probably flushing your nutrients through the soil before the plants have a chance to use them. So I think that the add a little extra water strategy is something that's days are numbered at this point. Certainly hope so. There's been a pretty strong push in recent decades to irrigate based on measurements of evapotranspiration. So if you can measure the environment, if you can measure the humidity and radiation and temperature and some of those things, you can see the Penman-Monteith equation there, then you can get an idea of the maximum amount of water that the plants could use. And then if you know something about your plant type and your crop type and what growth stage it's in, then you can get a pretty good handle on how much water that crop is pulling from the soil. Now, the big problem with evapotranspiration-based techniques is that you really have no ground truth for that, and if you have some error in your calculation of potential evapotranspiration or some error in your crop coefficient, then you can have pretty substantial cumulative errors in plant water use over the course of a growing season. So it's maybe sometimes better to measure the soil water status directly. So if you know how much water is in the soil or the potential energy of that water in the soil, then that gives you a little bit more direct method of understanding when you need to turn your pumps on or turn your irrigation off. So you can either measure water content or water potential. So they're both measures of the soil water status, and both of those can tell you if the soil is at an optimal moisture state for plant growth. But they are different measurements. So if you, for instance, installed some soil moisture sensors and simply measured the water content, this is a pretty easy measurement to make. There are a wide variety of soil moisture sensors out there, from neutron probes to TDR to the capacitance measurements. Pretty easy measurement to make. And you can, well, let me back up and say that the water content at which you would turn your pumps on and the water content at which you would turn the pumps off are different for each soil. Each soil holds water differently, and so in a sandy soil you're going to be irrigating to a much lower water content than you would be in a high clay soil. But it is possible to determine where those full and refill points are simply by looking at the drainage curves. Okay, you can understand field capacity and where the plants begin to stress by looking at the soil moisture dynamics, or you can determine that by measuring some plant characteristics like plant water potential or other characteristics that tell you about the water stress state of the plant. Once those full and refill points are known, then the water content measurement becomes very useful and very easy to use. And in the graph that I've shown up here, this is a typical trace that shows some soil moisture sensor data, shows volumetric water content on the y-axis and time on the x. And you can see the frequent irrigation events. Well, those irrigation events, in this particular case, are filling the soil too full with water. There is an inflection that you can see in the drainage curve. Let me get the mouse here. You can see that as the soil drains down, okay, this is draining, this is water that's being lost from the root zone. Well, eventually that drainage starts to level off, and this is what you could identify as being pretty close to your field capacity. And so you really would want to only irrigate up to this level, okay, and let your soil drain down, and the plants pull the water down significantly lower than that. So it's pretty clear from the data in this graph that there is a lot of leaching or drainage going on, where each time the water content, each time the soil is irrigated and the water content is brought up above that field capacity point, this steep slope here, this steep drainage slope, shows you that you're losing quite a bit of water. But one of the key questions is, how much water are we losing here? How much drainage are we getting? And it's a little bit difficult to tell simply from a water content measurement. Here's another graph that shows a field with very frequent irrigation, and you can see that the water content stays more or less stagnant, stays pretty constant across time in this field. So just from these data, would you be able to tell if water or nutrients are being lost from the root zone? Well, I would argue that you wouldn't be able to tell for sure. You have a pretty good idea that yes, you're probably getting some drainage, but being able to quantify that and being able to say for sure is pretty difficult. So we will get back to this particular data set later in the talk, and I'll show you how you can use electrical conductivity along with the water content data to get a better handle of what's happening below the root zone. So, as I said just a second ago, you can measure water content and try and empirically determine a full and refill point where you would turn the water off and then turn the water back on for irrigation, or you can measure water potential. Water potential in some ways is a little bit easier to use because the water potential levels that plants begin to stress and lose yield at are pretty well known. There's a large body of agronomic literature out there that tells you the water potential levels that are optimal for different crops, and you can see some of these references here that point to the agronomic literature. And so it really is easier to determine full and refill points because those full and refill points are the same water potential in all soils. So from that standpoint, water potential is quite a bit easier and quite a bit more convenient, but it tells you even less about how much drainage you might be losing through the bottom of the root zone, and it doesn't give you any information about how much nutrient or how much fertilizer you might be flushing through your soil profile. So again, you really can't tell some things. You can tell a few things. You can tell some things about plant water status with water content and water potential, but you can't tell if fertilizer is being leached past the root zone. It's really difficult to get a quantitative measure of how much water is being leached past the root zone, and you certainly cannot tell from water content or water potential measurements alone if you're having salt accumulation or soil salinity buildup. So that's why we want to tie in now electrical conductivity with the water measurements and see if we can't do a better job of irrigating. So let's switch gears a little bit and talk about electrical conductivity. Let's talk about the three types of electrical conductivity, and let's talk about the measurements that we can make of those three types and what those tell us about the soil. So first, just a review of units. The unit of electrical resistance is an ohm. Conductance is 1/ohms, and so that's a mho, or these days in SI units, it's a Siemen. Okay. The most common units of electrical conductivity are decisiemens per meter, which is the same as a millisiemen per centimeter. So you'll see those interchangeably. You'll also see millimos per centimeter. That's the same as a decisiemen per meter or a millisiemen per centimeter. But today we'll talk in terms of decisiemens per meter as our unit of electrical conductivity. The salt concentration in water is pretty close to directly proportional to the electrical conductivity. So you can see in the graph there that as the salt concentration increases, the electrical conductivity increases in an almost linear fashion. You'll also see that the osmotic stress, or the negative of the osmotic potential, increases in a relatively linear way with the salt concentration. So what this means is that if we can measure the electrical conductivity of the soil solution, then we know the salt concentration of that soil solution. So you can almost use salinity and electrical conductivity interchangeably. I'll talk in just a minute about which of the electrical conductivity measurements we can actually use as a proxy for the salinity of the soil. So I've spoken and said that there are three measures of electrical conductivity. First of those is the saturation extract EC, and this is, in this talk we'll use EC with a subscript of E, so that's the extract EC. This is the electrical conductivity of water that's been removed from a saturated soil. So bring the soil to saturation, remove some water, and measure the electrical conductivity of that extract. EC sub B is the soil bulk EC. The bulk EC is the electrical conductivity of the soil, water, air mixture. So the bulk mix, this is the electrical conductivity of that. EC sub W, or you can sometimes see that as EC sub P, is the soil water EC. This is the electrical conductivity of the water in the soil if you were able to remove a sample of that water. So this is interchangeably called pore water EC. So if you're used to pore water EC, the soil water EC is the same measure. So as I mentioned, the saturation extract EC is just the electrical conductivity of the water that's been removed from a soil that has been saturated with deionized water. Because the soil is at a constant water content, it's at saturation, okay, this is a quantitative measure of the salinity of the soil. So ECE, or saturation extract EC, is the measure of electrical conductivity that tells us the salt status or the salinity of that soil. It also tells us what crops will grow in that soil because that's determined by the overall salinity of the soil. And this is the electrical conductivity I think that most of us are familiar with, are most familiar with. If you send a soil off to the lab to get characterized for nutrients and other things, then they will send you back a measurement of EC. That's generally the saturation extract EC of that soil. And you can see that if you know the salinity of the soil, you can choose the correct crop to grow on that. And again, you can see on the left side here, there's a little table from Mark Van Ursel publication that shows the saturated paste extract, which is the same as the saturation extract EC, and what those different numbers mean in terms of the salinity of the soil, what those salinity numbers mean in terms of what kind of crops you could grow on those. So again, the saturation extract EC tells you about the soil salinity. How would you measure this? Well, it's a pretty simple measurement. You collect a soil sample, you take it into the lab, you saturate it with deionized water. That's sometimes easier said than done. Achieving a true saturation is not the most straightforward thing, but if you can do a pretty good job, then you can get a good measurement of the saturation extract EC. Once you've saturated the soil, then you use a vacuum and some filter paper in a funnel to remove some of that water, to remove the water when the soil is saturated, and then measure the electrical conductivity of that water sample with no soil in the system. That's the saturation extract EC. So I put a note in here that says that the bulk EC and the water EC are the same in a water sample with no soil matrix. So you're measuring the bulk or water EC of that sample that you've removed from the soil, and that gives you your saturation extract EC. Okay, now let's switch gears and talk about the bulk EC. The bulk EC of the soil is the electrical conductivity of that whole mixture of soil, water, and air. So this is related to three things. It's related to the total salt in the soil, which is better measured by saturation extract EC. It's also dependent on the water content of the soil, and it's dependent on the soil physical and, in some instances, mineralogical characteristics. So this is something that varies with 3 different parameters instead of just 1 parameter. So by itself, the bulk EC is not very useful for characterizing the salt status of a soil. Unfortunately, the bulk EC is the only type of electrical conductivity that can be measured in situ with electrical conductivity sensors. So in many cases, the saturation extract EC is more useful. In many cases, the pore water or soil water EC is more useful, but we cannot measure those things directly with an in situ sensor. So we have to measure the bulk EC and then try and do some calculations and use some models to get those other types of EC. It's unfortunate, but there's still not a reliable way of doing that yet. Although some will tell you there is, we haven't seen it yet. Switching gears again, now let's talk about the soil water EC. The soil water EC is the electrical conductivity of soil water if you could remove it from a soil sample and measure it. If you could pull that water out of the soil at whatever water content the soil is at and measure a sample of that, that would be the soil water EC. This is the EC that directly affects the plant. This is what the plant is sensing in terms of osmotic stress and osmotic potential. It's also an important variable because that's what we're going to use in our leaching fraction calculation that's coming up here in a few minutes. And then again, a note that at saturation, of course, the saturation extract EC is the same as the soil water EC. Remember, we're just pulling a sample out at whatever water content level, but if we're at saturation, the sample we pull out is the saturation extract EC. So only at saturation are those 2 things the same. So how might we measure the soil water EC? Well, there are a few ways to do that. It is possible, if your soil is moist, to use a suction cup sampler or a lysimeter to remove a sample of soil water, and then you could characterize its electrical conductivity and you would know the soil water EC. You can always also use a wetting front detector with an installed electrical conductivity sensor to get a more real-time measurement of soil water EC. You could use a drainage collector and pull samples from that and measure the soil water EC. But you cannot remove water from soil at low water content. It becomes impossible to pull a sample of water as the water potential goes down toward negative 100 kilopascals. And so these sampling techniques are only useful at high water content. There is another way to calculate the soil water EC, and this is by using the bulk EC measurements from an in situ sensor and the water content measurements from that same sensor. So if you have a multifunction soil moisture sensor that measures water content and electrical conductivity, then from those data you can calculate the soil water EC with some degree of error, and we'll talk about that more in just a second. So I want to run through a little thought exercise that you may have seen before. Galen Campbell gave a seminar on measuring electrical conductivity, and these slides in this example are actually from him. So you may have seen this before, but I think it's a pretty useful thought process to help us understand the differences between the 3 types of electrical conductivity that we've been discussing. So what we start with here is 1 gram of soil in 1 kilogram of water. So we weigh out a gram of sodium chloride and we mix that into a kilogram of water. And this gives us a 1 part per thousand or a 1,000 part per million salinity solution. So if we use an electrical conductivity sensor and measure the electrical conductivity of that solution, what we find is that turns out to be about 1.8 decisiemens per meter. Okay, this is the ECW, this is the electrical conductivity of the water. This is also the bulk electrical conductivity of this solution. If there is no soil present, if there's no soil matrix there to convolute things, then the water EC and the bulk EC are the same. So if you're measuring in solution, water EC and bulk EC are the same thing. So now let's add that 1.8 decisiemens per meter water into a washed sand that didn't have any salt in it before we're adding this water. So now we've added 1.8 decisiemens per meter water and brought a sand to saturation. So now what's our ECW? What's our water EC? Well, we already know that. We measured that. It's 1.8. What's our saturation extract EC? Well, we're at saturation. If we extract some of this water, it's 1.8, right? But what is our bulk electrical conductivity if we measure in the soil? Well, now our bulk electrical conductivity is nothing like 1.8 decisiemens per meter. In this case, in this sand, it's about 0.56 decisiemens per meter when we're at saturation. What happens if we allow this sample to drain? Well, our water EC, because we haven't evaporated anything, we have the same concentration of salt in that water, so our soil water EC is still 1.8 decisiemens per meter, but now we're down toward field capacity. What's our bulk EC? Well, our bulk EC is decreased even more. We're down at 0.09 decisiemens per meter at field capacity. So the key question that you're probably asking is, why is the bulk EC so much lower than the EC of the water? We know the EC of the water in that soil. We added it. Okay, so why is our bulk EC so much lower? Well, hopefully this diagram that I have up there will help elucidate that a little bit. If you look at the graph on the left, this is just solution. This is just water. This is what we were originally measuring. In that solution where there's no soil or air present, the electrons can travel directly through that solution via the shortest possible path, and that in that case the bulk EC is the soil water EC, of course. Once you add soil to that system, however, the bulk EC becomes much, much less than the EC of the water itself, because you can see the pathways we have drawn here. Now the electrons have to travel a more tortuous path, and it's a longer path that they have to travel, and that decreases the electrical conductivity. It increases the resistance to flow because they're having to flow through more solution. So in this case, the bulk electrical conductivity is maybe something like the soil water electrical conductivity divided by 3. Now, if we add in some air, if we go to field capacity, if we desaturate the soil and add some air voids, then these pathways are even longer, even more tortuous. And so depending on the water content and depending on the total surface area of water that's available to conduct those electrons, the bulk EC now is maybe 1/10 or 1/20th of the soil water EC. So this is why the bulk EC is really an indirect indicator of what the true salinity status of the soil is. And this is the reason that, of course, bulk electrical conductivity is never the same as the soil water electrical conductivity if you're measuring in a soil matrix. So let's talk a little bit about converting between those different types of electrical conductivity. I mentioned earlier that we can convert between those types if we know a few things. So we said that the bulk electrical conductivity is the conductivity that's measured by the sensor. We can predict the soil water electrical conductivity if we know that bulk electrical conductivity value and we know something about the soil water content or dielectric permittivity of the soil. So you can see the equation that I put up there is a very simple equation. This is the Hill-Horst equation that allows you to calculate the soil water EC from the bulk EC and a measurement of dielectric permittivity. So all of your multifunctional soil moisture sensors that measure dielectric permittivity and bulk electrical conductivity can be used to get a pretty good idea of what the soil water electrical conductivity is. So R5TE sensors, GS3 sensors, RS3 sensors make all those measurements that are necessary for the hill horse conversion. And our software will calculate that soil water EC from those measurements by the 5TE or GS3 automatically for you. It's a simple calculation to do. Unfortunately, this conversion is only accurate at high water content. Once you get toward low water content, once you get toward low dielectric permittivity, you'll see that dielectric permittivity is in the denominator. Once that dielectric permittivity value approaches C, then the bottom basically goes to zero, and you have big problems because your equation blows up. So you have to do this at high water content. We've limited our software to only do this above 10% water content. Measurements really are more accurate if you go higher than that. So this shouldn't really be used in low water content situations. Of course, most of the time, if you're in an irrigated situation, you're working in higher water content situations anyway, so it's generally not an issue. So how might we calculate the saturation extract EC? We talked on the last slide about calculating the soil water EC. How about the saturation extract EC? Well, we know that the saturation extract EC is the same as the soil water EC when the soil is saturated. And getting back to that saturation level is actually pretty easy if we know the volumetric water content of our soil, which our sensor gives us, and if we know the porosity of the soil. Okay, so if we know the bulk density of the soil, then we know our porosity. We can calculate that using the equation on the right. If we know that porosity value and we have a volumetric water content value from our soil moisture sensor, then we can use some very simple relationships to get back to the saturation extract EC, which of course tells us about the total salinity of the soil. And our DataTrack software will also make this calculation for you automatically if this is the parameter that you're interested in knowing. So now let's talk about using electrical conductivity to optimize irrigation. So there's a concept that's been around for many decades that's called the leaching fraction. And the leaching fraction is the ratio of the amount of water that has drained through the soil and been lost from the bottom of the root zone to the amount of water, the depth of water that has been added to the top of the soil. So it gives you the fraction of water that has been lost from that soil profile. This leaching fraction and maintaining a proper leaching fraction is pretty critical to preventing salt buildup if you're irrigating, especially with higher electrical conductivity or higher salinity water. For many years, farmers have tried to measure or estimate the leaching fraction and have tried to use that along with a graph like you see here and some knowledge of their EC of their irrigation water to get the right saturation extract EC in the root zone. So if you know the EC of the irrigation water, you know what your target EC is in the root zone, then you know what leaching fraction you want to shoot for. But getting good information about that leaching fraction is typically been very difficult. You can use instruments like lysimeters or the drain gauge that you see on the right to get an idea of that, but those are over a very small surface area and relatively expensive to use. So we would like a better way to get at our leaching fraction. And so what I want to present here is using salt as a tracer for irrigation water. And these ideas that I'm presenting here are not really new. In fact, our friend Richard Sturzacher, who works in Australia, came over and taught us a lot of these concepts. And so a lot of the things that I'll be talking about are ideas that Richard has worked on for several decades and has really come up with some good ideas here on how to optimize irrigation. So if you add water to your soil, that water carries with it some salt. That salt stays in the soil as the water is removed by plants. Other than some of the nutrients that are absorbed by the roots, most of the salts that we think about are stuck in the soil. Okay? So you can use those salts as a tracer to understand where your water is going. If your water is staying in the root zone and is being transpired by the plants, then the electrical conductivity in the root zone increases. If that salt is flowing through the root zone and being drained out the bottom of the root zone, then you will see that salt signature coming through the bottom of the root zone. So let's look at some really simple equations here and talk about what those mean in terms of leaching fraction. So the old way of thinking about leaching fraction was the depth of water that's drained past the root zone divided by the applied water, the depth of water applied. If you use the salt tracer technique, because that salt is a conservative tracer, the leaching fraction can also be calculated as the electrical conductivity of the applied water divided by the electrical conductivity of the water that's draining out of the bottom of the root zone. Okay, so those two ways to calculate the leaching fraction are equivalent. So what does this do for us? Well, first of all, it gives us a super easy way to calculate leaching fraction, but we don't really care about leaching fraction anymore. This gives us even more information. If you combine the two equations that tell us leaching fraction, you'll see the third equation there, that we can actually calculate the depth of water or the amount of water that is drained through our root zone simply by measuring the ratio of the EC of the applied water and the EC of the water that's drained through the profile. We also need to know how much water we applied, but if we know that information, we can get an idea of the amount of water that we've drained through the root zone. And this is pretty important because what farmer would not want to know how much water they're flushing through their root zone and how much water is being lost that they're paying pumping costs for that they don't really need to pay. So measure the applied depth of water, measure the EC of the applied water and the EC of the drainage water, and that gives you your drainage fraction, or the depth depth of water that's drained through the soil profile. So here's a pop quiz. We're not actually going to put a quiz on it, but want to throw this up there just to make sure we understand this point. Which type of EC do we need to measure to calculate our leaching fraction? So we said in the previous slide we need to measure two ECs. We need to measure the EC of the applied water, and we need to measure the EC of the drainage water. So for the EC of the applied water, well, we're measuring EC of water that's coming through an irrigation system, so we're measuring the bulk EC or the soil water EC, or the water EC. It's the same thing in this case because there's no soil in the system. The real question is, what EC do we need to measure in that drainage? Okay, well, we want the electrical conductivity of the water that's draining below the root zone. So in this case, we want ECW. So we would need to calculate that probably from the bulk EC. One more thing that is important to note here is that rain is almost free of salt, so it dilutes the soil solution. So if you're working in a system where you are irrigating, but you also have some rainfall that's adding to the soil water balance, then you need to take that into account. And this is an extremely simple mass balance, that the EC of all the water applied is simply the EC of the irrigation water multiplied by the depth of irrigation over the total depth of water that's come in either from rain or irrigation. So this is really simple, but it's important to do if a significant amount of the water that's hitting the soil is from rainfall. So let's work a real quick example here, and hopefully this will make a whole lot of sense for you. So if we measure the EC of our irrigation water, and we're irrigating with some middling quality water, 0.5 decisiemens per meter in the irrigation water, and then if we can measure the electrical conductivity of our drainage, in this case we're measuring 4 decisiemens per meter in the water that's coming out of the bottom of the root zone, we know that we've applied 20 centimeters of irrigation over the course of the season and that we've received 5 centimeters of rainfall. So first thing we want to do in the first equation is calculate the electrical conductivity of the overall applied water. So you can see that we use the mass balance there. It's very simple. 0.5, that's the EC of our irrigation water, multiplied by the amount of irrigation water divided by the total amount of water that's been applied to the soil. So what this tells us is that the EC of our applied water is 0.4 decisiemens per meter. Once we have that information, okay, then we can use that in the second equation where the depth of applied water, total depth of applied water in this case was 25 centimeters, 20 from irrigation and 5 from rain. Here's the electrical conductivity of our applied water, and here's the electrical conductivity of the water that's drained through the soil profile. So what this tells us is that we have applied 20 centimeters, 25 centimeters of water, and 2.5 centimeters of that water has been lost through the bottom of the root zone. So our leaching fraction is 10%, and the total depth of drainage water is 2.5 centimeters. So you can see that these are extremely simple calculations that have some relatively low-cost inputs that go into them. So, as I said earlier, if you have water content or water potential measurements alone, there's very little information about the amount of drainage. If you use electrical conductivity along with those water content measurements, then you can know your drainage. And the real beauty of this is that there's no longer any need for leaching fraction calculations. So what measurements do you need to make these calculations? Well, it's pretty simple. To measure the electrical conductivity of the irrigation water, you can simply screw in a ES2 electrical conductivity sensor into your irrigation lines that will measure the EC of the water that you're applying. You need to know the depth of water that you're irrigating, so you would put a rain gauge under your center pivot or under your dripper or however you're irrigating. You would also need to know the depth of rainfall that's supplementing your irrigation water, so you would put some rain gauge above or to the side of your irrigation system. Then you need to know the electrical conductivity of the drainage water. And so you could get that information from a pore water sampler if you needed to. You could get it from a lysimeter or a drainage collector, but probably the more common way of doing that is with a multifunctional water content and electrical conductivity sensor that measures bulk conductivity, measures volumetric water content, and uses Hill-Horst equation or Rhodes equation or one of the other equations to calculate the soil water EC of the drainage water. Okay, so switching gears here, we're switching gears a little bit. Here's another pop quiz. What EC type do you need to measure to understand the salt buildup in your soil or the salinization of your soil? Okay. Well, the answer to this is it's the quantitative one. The saturation extract EC is the type of EC that tells you about the total amount of salt in your soil or the salinity of the soil. And this is the one that you would use to understand if you're building up salts in the root zone and causing problems. So this is just a little conceptual exercise that shows us how we might use those saturation extract ECs to understand if we're doing a good job of irrigation on a more qualitative sense. So you'll see that each of these scenarios has a sensor measuring bulk EC but calculating the saturation extract EC in the root zone and below the root zone. So in the first case, there's no salt accumulation below the root zone, which means that we're probably draining too much water through the soil. What you'd really like to have is the second condition where the saturation extract EC, salt accumulation in the root zone is non-existent, but you're starting to build up salts below the root zone. This means that you're doing a pretty good job of flushing the salt through the root zone to the below root zone regions where it's not causing any problems. If you see something like scenario 3, where you're accumulating salt in the root zone and only in the root zone, then you know you don't have enough leaching fraction and you need some immediate irrigation to push that salt through the profile down below the root zone before you run into problems, some sodium toxicity or something. If you're accumulating salt in and below the root zone, then you're probably right on the borderline. You probably need to increase your irrigation a little bit to push the salt down through the root zone. So this is just another example of how you might use the saturation extract EC, in this case, to make sure you're not salinizing your soil. It is also pretty common in the horticulture industry and the high dollar cropping and intensively managed cropping systems, for instance, nurseries and greenhouses, to measure the soil water EC, or in this case, the substrate water EC, to make sure that that electrical conductivity is in the optimal range for the plants. In these systems, these are generally irrigated with high quality water, and most of the electrical conductivity that you see is from the applied fertilizer, from the fertigation. And so it's pretty easy to get too much nutrient solution, too many ions in that solution, and build up the electrical conductivity if you're not careful. And so it is pretty common to use that Hill-Horst equation or some other to calculate the water EC, which is what the plants are feeling, of course. That's what the plants care about, and optimizing that from a bulk EC and water content measurement in those substrates. So getting back to this data set that I showed you earlier, if in this case you were just measuring the water content of the soil, you really don't have any indication of nutrient leaching or any indication of drainage. But if you couple these water content data with electrical conductivity data, then you can see pretty clearly that you're leaching nutrients through the root zone. So the blue trace here is the 10 centimeter trace, and so there was a fertilization event here that increased the electrical conductivity, okay, even though we didn't see any increase in water content. And you can clearly see that this electrical conductivity decreases as the fertilizer gets pushed and leached down to the 30 centimeter level. So the 30 centimeter EC increases, and you can see that there's enough water running through this profile that nutrient solution, that fertilizer, is being leached down past the 30 centimeter level, past the root zone to 70 centimeters, and eventually it's getting flushed out even from the 70 centimeter level. So if you have this electrical conductivity measurement along with the volumetric water content measurement, then you have now a clear indication of nutrient leaching, and you know pretty darn well that you're pushing water past your root zone and getting quite a bit of drainage through that system. And here is some data we collected on a farm out in the Columbia Basin. This is an irrigated farm under center pivot irrigation, and you can see here again that after the fertilizer application in the root zone, this is the red trace is 1 foot depth, that's in the root zone, and then the 3 foot depth is below the root zone. You can see that the saturation extract EC shot way up after the fertilization, but now it's decreasing because it's being flushed into the lower levels. And you can see that at the 3 foot level, the saturation extract EC is increasing, which is an indication that even though this is a pretty conscientious farmer, they're applying a little bit too much water and flushing their nutrients down below the root zone. So we have a pretty clear indication here that we've got some nutrient loss in the EC data and pretty clear indication of drainage. And in fact, when you do the drainage calculations using the salt balance here, you'll see also that there's quite a bit of drainage going on, even though this farmer actually pays quite a bit of attention to his irrigation regime. So that's what we had to talk about today. I want to leave you with a few take-home points that are the important things that I hope you would take from this virtual seminar. The first important part is that there really are 3 different measures of electrical conductivity that all contain different information. And I'll make the statement, I didn't make it before, but I meant to, that these are the source of considerable confusion. In fact, I would say that 7 or 8 years ago when I first started looking at these things, it was really difficult to sort out what was in the literature. When people are talking about electrical conductivity, it's difficult to understand if they're talking about bulk or pore water or saturation extract and what those things mean. So Just make sure you understand that the saturation extract EC is what tells you about the total salinity or the total salt in the soil. That's our quantitative measure. Bulk electrical conductivity is the only electrical conductivity that a sensor can measure directly. Unfortunately, it's variable with water content and soil type and salt, and so it's a little bit convoluted, and you have to make some calculations to get the more useful information from our third type of electrical conductivity, which is the soil-water electrical conductivity. Which the soil-water electrical conductivity is what plants sense. That's what tells you if your plants are beginning to stress or are going to end up with some toxicity. And this is also the type of electrical conductivity that we would need to measure or calculate to make that salt balance drainage calculation that I've been talking about. So the next take-home point is that this salt balance concept that we've been talking about at Decagon with Richard Sturzacher and Galen Campbell and now myself is a pretty convenient method to determine your leaching fraction and the amount of drainage. The other methods that we have available to measure the amount of drainage are pretty expensive. It's not very expensive to do this salt balance, and it seems like it's a pretty robust measurement. So we can use EC to calculate our drainage. We can use measurements of EC to prevent soil salinization, and we can also use EC measurements to prevent nutrient leaching. And I think these are three pretty important things that are important to people who are engaged in irrigated agriculture. And hopefully you guys have found this pretty interesting. So thanks for attending, and I will be available to field any questions that you may have. If we don't get to your questions in real time, then feel free to go ahead and send those in, and anything that we don't get to, we will answer via email a little bit later. Thanks a lot.